Okay. Alright guys, this is what my talk today is going to be on, the P versus NP problem. I'm going to see what its implications are. But before we start, does anyone heard anything about this, or what do you?
It exists.
Okay.
And that we can't cancel P to get n equals 1, because that's
No.
reason.
That would be weird. Yeah. It's okay. Anyone know anything about like basic functioning of computers or anything? No? Okay, so maybe my talk would be that boring. Because if you did know anything, then it would be a little bit, maybe even erroneous at some point. But this is a very important problem in computers, in computational science, and even in actual mathematics as well. And before we start, we're going to look at what the role of computers are in modern physics today, and talk about the applications, and then talk about computers in general, before we actually move on to specific problems in computational science that demonstrate the way they think about things. And then we're going to the actual P versus NP thing, the implications, and as I mentioned in my abstract, there will be $1 million for you to win if you understand this talk. So okay, you guys all know that we use computers to run simulations of things in physics, and maybe I hope you guys can talk about a little bit, maybe turn this into a bit of a discussion since my talk is a little bit short. So have you specifically run any simulations on any, well I know you have with your centrifugal force thing, Coriolis force, yeah.
That strange attractor, I had to do a computing, like had to write a program to simulate how strange attractor evolves with time last year.
Alright.
So there were 3 differential equations. I solved this numerically on Xcode using C++ language, and then plotted X versus time, Y versus time, X versus Y.
Right.
Because you can't solve them analytically. Well, even though I did last time. You can't solve them analytically, and people normally just write a program to solve it numerically.
Yeah. And do you know actually where, I wanted to ask you about this last time, but do you know where the Lorentz attractor actually came from, and how Lorentz actually discovered it?
I didn't. Well, I have read about it, but forget.
Well, actually what happened was Lorentz was working on meteorology at the time, and he was modelling a problem of climate and weather, a weather system and how it changes. And he was looking back at some data he had before, and he entered the data again, but this time he rounded off the values to 3 decimal places instead of writing out the full expression, and he got a completely different result. And he checked his program and realised that if the initial conditions vary just very slightly, then you get a massive difference in your outcome, which is what the whole idea behind chaos and strange attractors.
Yeah.
Okay, so there's that in climate and atmospheric physics, and then we have it in cosmology when we're trying to, for instance, model or predict data from the CMB, as I think we went to that talk by Penrose, where he's talking about statistical analysis of all the fluctuations and things that happen in the microwave background.
In Astro, we could use it for like white dwarfs. I did it practically on second year.
Oh yeah.
Where you use it for the equilibrium equation of the white dwarf to predict what would be the maximum radius and find computation of the Chandrasekhar radius. And then the same for neutron stars, using this Volkov-Oppenheimer, Born-Volkov-Oppenheimer approximation.
And so do you make a visual?
You just plot like your radius versus mass, or the density versus radius and stuff like that. And this gives you this famous plot that as the mass increases, your radius of the star decreases until you reach the threshold, and then it collapses, which is the Chandrasekhar radius.
Right. So yeah, we start to see that this is useful to get a feel for things, because that's a problem in our second year stats page, where we have to work it out analytically with a very rough estimate, and that doesn't quite give you an accurate answer. So we need to turn to computers to solve these kind of problems. And we also need it for data storage and stuff with particle accelerators and other devices. And actually, CERN is responsible for bringing out the World Wide Web. Tim Berners-Lee worked there, and as a result he needed to he wanted to come up with a way to allow people to give information to each other across the world. And one of the ways is this idea of hypertext markup language from document. That's one of the very first browsers, Netscape. I don't know if anyone's old enough to remember that. And one of the things computers are doing now, they're becoming so advanced that just a couple of years ago I saw this news article. And what happened is that these guys at Cornell have come up with a way of getting a computer to record data from an experiment and then derive the laws of motion entirely on their own. So what they did was they did it with a pendulum, and then they plotted the data from the pendulum, and then they got the computer to come up with the best fit, and then it's working out all these things. So in some sense it's taking over our lives. Maybe it'll take over all our jobs, and there won't be any need for us anymore. But when it comes to the basic matter of the thing, computers are, okay, they're getting more and more intelligent, and some people have predicted that in about 20 years from now, they will be as advanced as human beings, and there will be this melding of our society and what we think of as a computer together to get this a new cultural dimension. And this is called a singularity.
Hi, I'm sorry.
And like the usual form of singularities, we don't want either. So we come up with the idea of a Turing machine. And a Turing machine is basically the most basic concept of what a computer is. It came up by the famous mathematician Alan Turing, I think in the 20s. And he came up with this idea at a time when technology wasn't sufficiently advanced that he thought this was a concept that wouldn't ever be realized. But actually today, with our methods of storage, we have come very close to actually approximating this device. So in some sense, all modern computers today, we can get rid of all the extra features like the graphical processors, and just think of them as these machines that just read the tape and just change the readings on it one by one by reading the instruction table. And we come on to this idea of computing time. When you have a computing problem, the way you think about it is that you break it down into a set of steps, and then you get the computer to go and crunch it, and it comes up with something in a given amount of time. And this time is often related to the number of steps you have. And we have this concept called polynomial time, in which the computer crunches things and works things out in a time proportional to a polynomial of the number of steps. And of course, I say as n tends to infinity because you can have n to the 3 plus n squared plus whatever, but you only need the higher order in the term. And that tells you, in what sense, how complex the problem is. And an example of this is the greatest common divisor thing, algorithm, and it's done by, it was formulated by Euclid sometime BC, I can't remember when, but if you give me, shall we say, just give us 2 4-digit numbers and we'll try and work this out. Okay, 2 fairly easy numbers, so we won't get into a bit of a mess.
2001.
2001, I doubt this might actualize, but, and another one?
3892.
3892. I doubt this is going to give us a factor higher than 1. That is okay.
Oh, 3891 is better.
Okay. Okay, so we want to find the highest, the greatest common divisor between them. So the way we started by doing this is that we find out how many of these go into this. So we write down the high number, and we say it is something times 2001, and obviously the biggest number we can put in is 1 at this stage. And we find what the remainder is, and that happens to be 1,890, right?
Yeah.
Okay. Next, we move on to this number. We bring it over here. And then we have to find out how many times it goes into 1890. And obviously that, again, is going to give us a 1. And then we're going to get a remainder of 111, right? We bring that all the way down again. So it's going to be something like, what?
16?
16?
Yeah, probably.
So if you do 16, it's going to give us 160, it's giving us 1776. So that's going to give us a difference of 114. No, yeah, 114, right? Yeah. Please correct me if I'm going wrong here.
You probably mean
No.
17 in that case.
17.
Yeah.
Oh, right, okay. So that would give us another 16, that would give us 1792, and that would give us 898. As our difference between
Yeah.
1792 and this.
Do you have here, there 111?
Sorry?
It is, oh yeah, it
Yeah,
is
the one of
111.
them is there.
Mhm.
Then we need take a 111 here, that's going to be 1 times 98 plus.
Sorry, I think that 1 times 17 is probably wrong. But
Oh, right, yeah, sorry, I've done something.
Can you sort of do it
ridiculous
again?
on that.
Yeah,
Right.
it should be 17.
So it should be 3.
Yeah.
And this is what, 30,
37?
plus 0, so that tells us that, tells us 3 is going to be our highest common factor between these two, the greatest common divisor. And this is the simplest form of the algorithm that can be crunched in Hollow minimum time by a computer. Okay, and another one is obviously going to be a matrix multiplication. And this is a problem that goes as n cubed if we do it the classical style, where we do row and column multiplication, where we take each element and we go up, along, and down. But there is another method which I found too difficult to understand, but it gives it to us in marginally less, which is n.2376. There's one before that, which is n to the 2.8, but they keep finding clever ways of going about this business. And we come to non-P-class problems, and this is going to be things like the prime factorization of integers. And if we have a number, this is what I picked off Wikipedia because this is the best source I could find on this. But if we have a number and we express it in binary, and the number of bits it has, in the sense is the number of digits that it has, the amount of time it will take to process, to factorize this number will go as an exponential in that expression given there. But someone interestingly found out rather recently, about 15 years ago, with a quantum computer, you can actually factorize prime numbers in polynomial time. But unfortunately, the only thing you can do, the highest number is being able to factorize in polynomial time is 15. And maybe they'll get on to a higher number sometime soon. But this is something I'll come on to a little later in the talk. If you've got any, yeah.
Could you explain how to get the time for this algorithm?
I think the way it goes is